say, or something like that. So this bit that I'm showing at the moment, this is the session 2 examples and making TensorFlow work for pins. Okay. So for the most part, you can use a lot of the black box functionality if you're doing a relatively simple problem. And what do I mean by relatively simple? You just want to do some kind of gradient-based optimization process, minimizing a simple loss function, which is probably defined in terms of integrals and derivatives of some trial function. So the neural network itself that we're using to solve our PDE, I mean, this is basically just a typical TensorFlow model, the same way that you would define it for a simple implementation problem. But the only difference is because I'm solving, in this case, a PDE with a Dirichlet boundary condition, instead of putting some penalization in the loss, I multiply the output of my neural network by a function which is 0 on the boundary so that I don't have to worry about boundary terms. So the fundamental object within this kind of approach is the layer. And layers are basically the best way in this, we're trying to take advantage of the black box of TensorFlow. I mean, any calculations that are going to go into your training process, you should be putting inside a layer. So the functionality is always more or less like this. You define it as class, whatever you want to call the layer. This goes into the tf.keras.layers.layer environment. You initialize with whichever parameters you wish, and the calculations that you do within the layer go inside call. Okay, so obviously self is self. This is a Python class. Then the inputs will correspond generally to outputs of other layers within this framework. Okay? Then within here, you can do whichever calculations you want to do a simple cutoff function. So I have ut, which is the output of the previous layer of my neural network. X is the input of my neural network, and then I basically just multiply the output of the previous layer by this guy, which is equal to 0 on the boundary. Okay? So once you have your layer defined, then you can use it just like any of the black box layers. I mean, TensorFlow has a bunch. At the level of using a neural network to solve a PDE, I don't tend to see much beyond dense layers. So the kind of layers you would use in a fully connected feed-forward network. But for other applications, I mean, they have a whole bunch. You can just go TensorFlow layers, and then it has the whole list, all of the parameters you can put in, and so on and so forth. The other way that we can use layers is to define the loss itself, because I mean, the sort of native functionality of TensorFlow isn't based on using derivatives in your loss function. It's just based on input-output pairs. So normally you would have some kind of data where you have inputs of some kind of data and then the outputs of some kind of data. And according to a loss function, which compares the predicted value by your network and the value from your data, it gives you a loss function. And then this is what's minimized. If you want to try and sort of hack TensorFlow to make it do things involving PDEs, then this approach can work for simple problems. So the same way that we defined the layer to give us the boundary condition, we define a layer that outputs our loss. So we stick our neural network, which is going to be our solution, into the initialization of the layer. Then we can just do all of the calculations that we want to produce the loss itself, right? This is just going to be a number. In this approach, I mean, if you want, you can make your loss function depend on some parameters. But if we're just thinking of solving a single PDE using Monte Carlo integration, this input really doesn't have any effect. It's not that it doesn't have any effect at all, in fact, right? I create my data points, which is my Monte Carlo sample here, which I use to evaluate my residual. Now, the whole TensorFlow functionality is based on minimizing a loss function, which is always of this form. Okay, so you have y true. This corresponds to your data. Y pred is the output of your neural network. So for a mean squared error loss, it would just take the 2 away, square it, and sum over all of the entries. Okay? Now, because the output of our model is going to be the loss itself, the thing that we want this loss as far as TensorFlow is concerned to be is just the value of y pred, the output of the layer that gives us our loss. And within this framework, now we can use all of the black box functionality essentially that we want from TensorFlow. We can use inbuilt optimizers. We can use callbacks. We can use all kinds of different things within it without having to really go too far beyond the native functionality. Okay. So this was the example that I showed. You get this object. So when you do fit, where do I have it? Here. So when you fit the model, okay, it automatically optimizes over every single variable which is inside the loss model. Now, one of the things inside the loss model is the neural network itself. So the variables of the neural network are inherited into the loss model and they automatically optimize over them. Okay. And then in this object history, which I define here, this gives you a class. And then the most important object in the class is the history dictionary, which automatically records things like the loss. Okay. So before talking about a different way of approaching these kinds of problems, and were there any questions or doubts on how this works? No? Okay. So the next thing that I want to show is a sort of much more versatile framework. So you lose a lot of the black box functionality, but it can be very useful for doing more advanced problems or problems where you have stranger things going on. And the two examples that are easy to see where this kind of approach fails is when I mentioned this least squares optimizer. So the idea is that you understand that your loss is quadratic in certain variables in your neural network. We know how to minimize quadratics, so you do linear algebra essentially there, and then gradient-based optimizers everywhere else. Now, we managed to implement this idea into this kind of framework, but I mean, it was a disaster because essentially it differentiates through a bunch of operations that it shouldn't, and then it takes forever. Okay. So if you want to have more control over the way that your model is being trained, then you need to be thinking about other approaches. And another approach, which I'm thinking of discussing if we have a bit of time afterwards, there are some formulations based on min-max problems, right? Rather than just minimizing a loss function, you have a loss that depends on two things. You want to maximize with respect to one thing and minimize with respect to the other. And this doesn't really work well natively within the fit environment. It can only really do one or the other. So in order to give you guys a kind of skeleton around which you can build many, many types of optimization problems with a lot more control and a lot more flexibility, I have another document, which is if you go to the GitHub in session 3, and so now we're leaving Jupyter because now things get a lot more complicated to put into a notebook environment, but we're going to go piece by piece and see how these things work. So the file that I'll be considering is this one here, example simple interpolation. So I'm just going to be looking at a really simple interpolation problem with a mean squared error loss, given some data. In reality, if you want to solve this problem, you'll use the black box. Okay, so what I'm going to show you, this other framework, it's not to solve this problem. It's so that you can see the kind of ingredients of how you can make a much more custom optimization process in the simplest case possible, and then we can go adapting to other problems. Okay. So here, I'm not sure if you can see very well. Okay, so what I'm going to do, so first I'm just going to run these guys. So all I'm doing here is defining some training and test data. Okay, so I have my training data, which is given by 100 samples. My outputs are going to be basically sine plus a little bit of noise. Okay, so these are the same samplers that we used in the TensorFlow environment before. I'm going to manually define some validation data, which I'm calling X test and Y test. And here I define a function which builds my neural network model. Okay, so in reality, if you're only training one neural network, it doesn't make sense to define this function. But if, for example, you want to compare many, many different neural networks or many different optimization schemes, it might be useful to use this kind of functionality. So you can just easily produce more and more models over and over again. Now, after this, I define a big class. Okay, so it's quite a fair few lines, but I'm just going to run it, and then we're going to go line by line, essentially, and see what this class does, okay?
You don't see from HeI, just connect to the Zoom link, then
So I'm not going to claim in any way that this is the optimal way of how to do things, but at the very least, what it contains is all of the different ingredients that you might need, and you can generalize to other problems. Okay, I organize things sort of like this, and if you look at the other examples from, for example, the first session, I put some snippets of code. They all more or less follow this structure, but with different variations within them. Okay, the first thing, this is just to initialize basically everything that I'm going to be using in my training scheme. Okay, so what I'm going to have, I'm going to import my data. This is somehow the obvious part. And what I'm going to want to do during my training is record my loss at every iteration, my validation loss at every iteration. Okay, the number of iterations, but this can basically be ignored as well. So this is just so that I can access this data after I've done my training. Then similarly to the black box case where you have to define the optimizer that you want to use, I do exactly the same thing here. Okay, I'm deciding what my optimizer is. Okay, if, for example, you wanted to compare lots of different optimizers, well, you'd put this as some kind of entrance when you're initializing the class here. But I'm just thinking of a much simpler problem. And I create my model here. So I've initialized my class. So now I can access it. I've called it T. So I have TU model. And let's just put it into some input so we can see that it works. Okay, so I can access all of these guys just by calling the guys which are inside my class. So the next thing that I want to do is define my loss function. Okay, so in this simplest case, I'm just thinking I have some inputs, which may be my training or my validation data, both for X and the Y coordinates. So I'm going to define my loss function. Okay, so here we see this is just mean squared error, nothing more interesting than that. Okay, in principle, I could make this as complicated as I want. Right, and this is easy enough to adapt to some kind of PDE approach. You would do something similar, but evaluating the derivatives with respect to X and so on and so forth. Okay. Now, I wrap this in a TF function. So remember, TensorFlow has these two ways of running functions. There's the eager mode, which is the default, which is just standard line-by-line evaluation. But if you decorate with @TF function, then what it does is it creates a graph, which is in some sense a much more optimized way of doing all of the calculations, which has some cost in creating the graph. But once the graph is created, it tends to run sort of the order of 5 to 10 times faster, as long as you put the same kind of inputs in every single time. So if we're doing any kind of iterative method or generally evaluating anything many, many times during a training loop, which is normal, right? We're thinking about orders of thousands, tens of thousands, maybe even more iterations. And this can save us a huge amount of time. So, okay, my loss function just takes whatever its input is, puts it inside my neural network. We find the residual and sum over the squares of all of our residuals. Okay, so this is straightforward. Now, because in this case, we don't have the sort of inbuilt black box training loop, we need to define some functions in order to make this work the way that we want. And of course, if we want to do a gradient-based optimizer, then we need to have the gradient, right? So I define another function, which I'm calling loss grads. And what this does is, again, it's a TF function because I'm going to be evaluating this thousands of times in principle. So within a gradient tape, I evaluate my loss, which is the same loss I have here, and then I get it to return the value of the loss itself. So maybe I want to save it and see how this thing is evolving, and the gradient of my loss with respect to U model.trainable weights. Okay, so the U model itself, so this somehow has a lot of class-like functionality, and if I do trainable weights, sorry, T.U model. Okay, so what we see is this big list of tensors. Okay, so in this case, it's just a single layer neural network. So really, I just have the affine map, which is on the inside of my activation function, another affine map outside my activation function. But these tensors are different sizes. So the way that the trainable weights thing is defined is you have just a regular list, and each element of the list is a tensor of a particular size. Okay? Now, when you use gradient tape over a list of tensors, it returns a list of tensors of the same shape, okay, at least in the case of a scalar function. So if I do loss grads, okay, we can evaluate this. So LG, this is going to be T dot loss grads. So what we see, G, again, is a list of tensors, okay? So the numbers aren't particularly important that we have here. You can see, okay, we have a little square bracket there saying it's the start of the list. This is going to correspond to the weights of the first layer. The next element corresponds to the biases of the first layer, and so on and so forth. Okay. And so within my class, I now have this loss grads function, which gives me both the loss and the gradient in the form of a list of tensors. And this list of tensors is of the same size as the list of tensors, which are my variables within my neural network. So now that I know how to evaluate my gradients, I need to know how to update my model according to these gradients. Okay. Now, here in principle, I mean, I could write whatever optimization scheme I wanted, right? So I call it one step, meaning one update step, essentially. So if I wanted to do some really crazy optimization scheme that's nowhere near the black box, I could define whatever method I want to update the weights in this kind of environment. But a lot of the time, I mean, the complicated part isn't the optimizer itself. You're still using some of the standard optimizers, but with other aspects that make your problem more complicated. So the way that you update your weights according to an optimizer, which we've specified before. So remember self.optimizer. This is just one of the black box optimizers, right? I mean, I could change this to SGD or Adagrad or any of the other ones which are there inside the native functionality. And the way that these work, so self.optimizer, whatever you've called your optimizer here, so dot apply gradients. Obviously, this is applying the gradients, which are given by G, the output of my loss grads. And then the guy on the right, these are the variables to which we're going to be updating according to the optimizer. Now, this functionality is a little bit simpler if G is a single tensor and I want to update a variable, which is a single tensor of the same size. But in this case, remember the trainable weights, this is a list of tensors. It's not a single tensor. And this is why we have zip here, because it kind of just joins everything together to make sure that we can do everything correctly. Okay. So we can manually see how this works. So I have G defined from before. So I can do, for example, t.optimizer, apply gradients, zip, G, t.umodel, trainable weights. Right? Okay, so this is really doing exactly the same as what I would expect this function to do. So just to see if it's actually made any difference, let's just look at the value of the let's go for this one, the very last guy in my trainable weights. So now I have t.u model, trainable weights, -1. And what we can see is that it's done an update. Right? But as I say, if you want to do a crazier update scheme, then I mean, this is the kind of place where you can do it. So for example, in this least squares based optimizer that I was talking about, and this is where I would do all of these calculations. I would construct this linear system that corresponds to the optimization principle for these weights with respect to which my loss is quadratic. I update that, and then I would do just a standard optimization over the rest of the loss with respect to the other variables. So things clear up to now? Yeah, very good. And then after that, so I basically have all of my ingredients that I need in order to evaluate my loss function. I know how to update my loss function according to the gradient, which I can also calculate within this environment. And now I just define a final command, which is saying, train my neural network for however many iterations. Okay. Now, if you're using the kind of black box functionality, you have access to all of these callbacks, right? So remember, basically, there's only two parts that you're really playing with when you use the black box, which are the evaluation of the loss itself, or any other kind of calculation which is used to create the loss, And if you want to do anything that's really outside of that, for example, change the way that you're optimizing, if you want to change your learning rates, if you want to record the best weights that you've obtained according to some metric and save them to access later, these all go into callbacks. Okay, I mean, in this kind of framework of solving these problems, at least as far as I've been able to play with it, I mean, there's no easy way to implement the callbacks into this, so you kind of have to do things by hand, okay? Which can be good or can be bad. I mean, it's good if you have to do it by hand anyway, then you don't need to work out how to put it into TensorFlow's language. But if it's something that does exist in the black box, then okay, you have to do it by hand. And this is just an implementation issue. So in this case, I'm not going to do anything particularly crazy. All I'm going to do is initialize my iteration number. And then while this number of iterations is less than whatever I say is my maximum number of iterations, while I increment this index, I do my one step. So remember, one step returns the loss as well. It doesn't just do the optimization, but it also gives me a number. So what this step does is it calculates my loss, calculates my gradients, applies the gradients according to the optimizer, and then returns the value of my loss, which is just a number. Then here, okay, this is kind of my very, very simple version of maybe if you want to do something more advanced in your training process, adjust the learning rate, whatever, then you could do it in this kind of, after doing your update. So I just update my loss list with my current value of the loss. I also evaluate my loss over the validation set. Then I stick that into another list to have access to this later. I update my list, which contains all of my iterations, and I just print some information, which might be nice to know. So once you have all of this, then things are really, really straightforward. Okay, I just specify how many iterations, how many neurons, anything I want to initialize here. And now I can just do my training by calling into my class. Okay. And now we see it's training, it's spitting out all the information I wanted to. And something that I've got no idea if this is an implementation issue on my side or if this is really something sincerely problematic with TensorFlow. I mean, when I've done this kind of problem, I mean, the stuff that exists in the black box, sometimes it goes much, much quicker doing it this way, which doesn't make sense. I mean, there may be something deeply wrong that I'm doing when I'm using the black box, but I mean, the time per iteration for an equivalent problem often runs quicker using this environment. I don't really know why. Okay, there's some strange things going on in the black box that are adding into time, and I'm not taking advantage of at the end. Okay. But once we have all of this, I have my class. My class has access to my previous values of my loss. I can do all the kind of plots that I want afterwards. So let's just see some nice little pictures. Okay, so I should have left it training for longer because I've got a really, really bad solution. Okay, but I mean, that's just an issue of having a very, very short iteration loop. Okay, so if we go again, let's see if it actually works this time. Yeah, okay, now it's doing what it should, right? We're seeing that the loss is going down. And actually, and this is one of the advantages of doing it in this environment. If you use the black box environment and you stop training in the middle like that, now you can't access this class, which has all of your previous losses, right? So you kind of lose all of this information. But by doing it this way, at least, because all of this information is in the class that I know how to access, I can stop training and I have access to all of this stuff, right? Okay, so now we see that this time it's trained reasonably well. So we can have a look at what my losses are doing. Okay, this is doing more or less what we expected. You always have this plateau at the start, which is somehow related to poor conditioning, drops down, and now it seems to be in some kind of equilibrium. Right? And things that I could do, for example, is I could stick something here to say, if my validation loss is no longer decreasing, let's just stop training because I'm not gaining anything. You can put any kind of functionality that you like into this framework according to whatever your needs might be. Okay. So with this, are there questions or comments? So as I said, I mean, it's not really typical to use this kind of level of personalization for the really, really simple black box problems, but we can see, and we'll move on to the other document that I have, how once you have this kind of framework, I mean, it's incredibly flexible. I mean, you can just sort of copy, basically everything I do is copy pasted from something very similar to this, and then you just have to make a few little changes here and there. So the other document, so the one that I'm going to show is slightly different because there's a few other little things that I want to show you that go beyond what's here. But if this is more or less morally example pins class, okay? So what you'll see here is that for the most part, okay, there's all kinds of extra little things that I've put in that I want to show you. But the setup is more or less the same, okay? I have this way of initializing my model. I have this custom layer now to impose my boundary condition because I'm thinking of a pins problem and I've decided I want to impose this guy. I initialize with whatever things I want to include as far as my training is concerned. Now, a few things that I add here, which I didn't add in the previous case. So if I'm going to be solving just, again, our favorite simplest differential equation, second derivative of u is equal to f. Well, what I want to do is know what my f is. So I call this right-hand side. This is just another function that I define within my class. At some points, now what I'm going to want to do is evaluate, or at least estimate my error. Okay, in this situation, what I could be thinking of doing is, I mean, I want to see if my method is working or not. So I compare it to a case where I know the exact solution. So I put my exact solution, which I know here. This is just a simple sine function. Maybe make this a bit bigger for people at the back. Okay. And now what I can do is introduce some other function where now what I do is I can estimate my H1 error during my training process, all within my class as well. Okay, so I define another function, I call it H1 error. And again, this just works the same way as the kind of loss itself works. I evaluate point-wise the error between my approximate solution and the exact solution on some fixed set of integration points that I've specified before, x exact. So I just take a midpoint rule to make life easy. Using gradient take to find the derivative, and now I just return the integral of the derivative of the error squared, right? This is the H10 norm for the problem that we're considering. Again, because I'm going to be measuring this error many, many times during my training, I'm going to put this in a TF function because this just makes things much, much quicker during the process. Now, in the example, or some of the examples I've shown before, the integration strategy that we've been using is Monte Carlo. Okay, so Monte Carlo, at least if you're in a simple domain, say a disk or a cube or something like that, okay, this is really easy to implement if you're using just typical random number generation using the TensorFlow random package. But I mean, sometimes you might want to do a more advanced type of integration, or maybe you have a strange geometry that makes sampling a bit harder. So in this case, what I'm going to do is define quad points, where this is going to be essentially my quadrature rule. If I had a more advanced quadrature rule, maybe I have points and weights. I can make it return both, whatever I like. In this case, what I'm going to do is, so remember when we were talking about integration strategies, and whilst there's a whole world of integration strategies, the simplest one for low dimensional problems that can improve convergence by reducing integration errors is going from regular Monte Carlo to stratified Monte Carlo. Okay, so we essentially take our domain, we partition it however we like, and then we take one point in each subdomain and evaluate our function at these points with a weight that corresponds to the size of the domain we're in. Okay, now, if we have a uniform partition of 0, 1, then what I do is define a mesh where this mesh is just a list of points. So if we say have 10 points, I think of the left-hand point as being, in each interval, as being the coordinate. Okay, so I have coordinates 0, 0 0.1, 0 0.2, up to 0 0.9, where each one corresponds to the element of length 0 0.1 starting at this particular point. Okay. Again, there's much more advanced integration strategies that you can bring in, but by defining this mesh, which I'm going to use over and over again, so I put it in the initialization, then my quadrature rule is I just take a uniform sample of the number of points I have, where the maximum value is h, the width of each of my elements. Then I just add this random variable to my mesh. Okay? And then this gives me a random point in each interval according to the mesh that I've defined before. Okay? So once I have all of these guys, so I know my right-hand side, I know my exact solution, I can estimate my error at any point during training. I know how to find my quadrature points that I want to use during my training process. After this point, I mean, it's more or less the same kind of process that we had before. Okay, so in the version that you guys have, you only have the Ritz loss. So for the deep Ritz, remember, we're talking about the minimization of the integral of half derivative of u squared plus f times u. Okay, so this is a useful loss function if you want to do approximation in H1, because the loss is basically a constant plus the H1 error. Okay, so this is a very nice loss to use if you're interested in good H1 approximations. So basically the same kind of idea as what we did before. So I take my sample according to my quadrature points. So because this is based on a random sample in the definition of quad points, this gives me different points at every iteration. Then same as before, all I need to do is evaluate my loss. This time my loss depends on the derivative of my neural network and not just the neural network itself. But I mean, this isn't a problem. I just do all of the arithmetic that I would do if I wanted to evaluate it on its own. So I evaluate my U model within a gradient tape. I take the gradient afterwards. And in this case, because I have a uniform partition, the weight that corresponds to each of my quadrature points is the same. So I can just use reduce mean. Right? If I have weights, which let's say it's W, then I would multiply this by W and do reduce sum, something similar. Okay, but this is easy enough to change. I'm just going to skip over one. I'll explain this bit, in fact. I mean, so again, so this is just to show you some other stuff. If you want to do a pins type approach, okay, exactly the same. We just take a higher order derivative as well by putting a gradient tape in a gradient tape. And we do some other calculations to end up with the loss. Okay, so I'll explain this bit in a second. So the way that I've defined in my version of the code that I'm showing up here is that I'm allowing, as part of the entrance to my class, I'm allowing myself to specify which loss function I'm going to use. Am I going to use pins or am I going to use Ritz? Okay. So by default, it goes as pins, but I also have things organized so that I can do Ritz as well. So exactly the same. I have these two loss functions defined. Depending on which one I'm actually interested in, I evaluate one or the other. And then I do exactly the same process, essentially. Okay, we can ignore this guy on inverse for now. I'll explain that in a minute. We obtain, oh, just realized I'm missing something here. We obtain the gradients of the variables that we're interested in, and we return the loss. And then afterwards, basically exactly the same thing, right? We do this one step, which tells us how to do all of the optimization we're interested in. And now within the training loop, again, more or less the same idea, but now, for example, I have this other guy that I want to measure, which is the H1 error, right? So at each iteration, I evaluate my H1 error, and then I put this into another list, which appears here, so I can access this and look at how this guy is evolving during the training process. Okay. Now, one of the things, if you wanted to do something like this within the black box, okay, so I have something which is another gradient-based guy that I want to evaluate, perhaps over different integration points. If I want to do this within the black box, I can really do this in kind of one of two ways. I mean, one of the ways would be to put this into a callback, which is how you can do a lot of things outside of the training loop. Or another way is to create another layer that gives you this metric, but then it needs to evaluate it every single iteration. Right? And you can find a way to extract that information during training. But it might be that, okay, if I'm doing 25,000 iterations, I only want to measure the error every 500. So I'm not expecting it to change a lot, and this introduces some cost on top. If I wanted to do something like that, then I could easily put, if I is equal to 0 mod 500, then I do this calculation. If not, I don't. Okay. This makes things nice and flexible. And then once I have all of this set up, I change this to Ritz. And then all of the process is more or less the same afterwards. Right, so I can set up my training loop and everything is going to go through. I specify the number of iterations and everything goes off as more or less as we expect it to. Okay, so just finish that there and show the pictures that come out. Okay, so here we see how our error is going. Things are decreasing relatively quickly, and now we're in this noise regime, which is more or less what we always expect to have. And if we compare the solutions, okay, here we have the exact solution and the final solution, and we see that they're more or less in agreement, at least. So are there questions and doubts up to this point?
Here, yeah, it was reasonably simple, right?
Mm-hmm.
Also allow some which allows some discontinuity in there, like
So in principle, I mean, the Ritz method in principle will always work as long as your f is square integrable, right? So it's not even required to be continuous. Now, and this is something that I haven't really touched on in the theory part, but I mean, there's one big problem with neural networks is that if you use a very smooth neural network, it's very difficult to approximate something that isn't smooth. Okay, so I mean, you must be all aware of the Gibbs phenomenon, right? If you try to approximate something discontinuous by Fourier series, then you end up with these oscillations that don't go to zero, right? This is the kind of thing that you normally expect to see if you try to approximate something discontinuous with a neural network. Right? So it's a very Gibbs type phenomenon. Now, it might be tempting to think maybe we should then use something with lower regularity to approximate the thing that we're interested in, right? And if for example, we want to approximate the absolute value function, maybe we should use something like ReLUs, right? Because a ReLU is a piecewise constant function. But if your loss depends on the derivative of your neural network, so your derivative is like a Heaviside function. But when you take the gradient of your loss, it's morally like taking the second derivative of your neural network. And the derivative of a Heaviside function, right, it's like a delta function. And then you can't integrate this, or at least you can't integrate it with quadrature. So then it becomes impossible for it to actually train because it's evaluating everything incorrectly. So I mean, there's a whole game about how to try and get neural networks to approximate low regularity solutions, because in some sense, I mean, the optimal regularity to approximate your solution isn't enough to do a gradient descent, right? If you're more regular, then it's hard to approximate. If you're the same regularity, then the derivative of the loss is probably going to be wrong. So, and this is a whole game in itself, but as I say, in principle, the Ritz method should work, but I mean, there's optimization issues and approximation issues that lie within that. Question?
If you wanted to use something to, for example, I have a 1D Landman equation, you have to change your method, or maybe the structure of your method.
Yeah, so yes, I mean, if you change the equation, then there's probably going to be a better initialization, a better architecture, a better activation function, a better optimization process, and so on and so forth. And a priori, it's not always clear what the best one is, right? I mean, a lot of it is just playing and seeing what works, more or less. I mean, there's really not a solid theory. I mean, for some very specific types of equations, there's been much more detailed work, but these ideas probably don't generalize to something which is really similar, right? So I mean, in some cases, there's a much more developed theory on what you should do, but I mean, for a general PDE or something like that, there's no magic bullet that says you should be using this type of initialization, for example. Okay, but within this framework, I mean, you can really change everything to be more or less. I mean, in principle, you could put any PDE into this kind of framework, right? I mean, I could easily change my neural network to be a two-dimensional neural network, I could change this residual to correspond to the wave equation, and I could put this into the program. But if I don't have the correct architecture, the correct weights in my loss, so on and so forth, maybe I don't get a good solution. Right? But in principle, you can do more or less everything. Okay. So are there questions, comments, doubts after that? Okay. So I mean, there's just a couple of really, really small changes that I would just want to make to this document to show you and how how flexible these types of approaches are, right? So one thing, for example, is if I have the Ritz method, now I can use the Ritz method as well if I have a Neumann boundary condition. Okay, so it might be worth writing this on the board. If I have, just thinking of a 1D case, if I have that my second derivative is equal to f and my Neumann condition at 1 is equal to g, let's say something like this. Now I can take my neural network with a Dirichlet condition at 0 and consider, I mean, it's basically the same problem. But now I add some other term, which involves the boundary. I mean, if we're in higher dimensions, this turns into an integral corresponding to whatever our normal derivative is. But I mean, this part of the loss is the same. This part is something which changes depending on the Neumann condition that you have, right? Now, just by doing essentially two tiny, tiny, tiny little changes in my code, I can change my Ritz method to this, right? I mean, I don't have to reinvent everything. All I do, I go back to where I've defined my cutoff layer. So I get rid of the guy that makes it equal to 0 on the other side of the boundary. Now I'll go into where I've defined the loss. So for this particular solution, so I put this as a reminder that I have here. So I know what the derivative of this solution is here. So I'm going to write an equivalent problem in the sense that it has the same solution, but now it's going to be based on a different loss function with a Neumann condition instead of a Dirichlet condition. So how do I do this? Well, now I just add this extra line here. And that's it. Right? And absolutely, well, basically no change, assuming I haven't made a sign mistake here. And now if I just stop the training to instead of leaving it for ages. And again, once again, I get a reasonable solution. Okay, so I can change the problem to something which, okay, a priori, this is quite a different problem, but I mean, it's not even a full line of code which I have to change if I want to implement this problem. Okay. So another thing that I want to show, so that, okay, there was this other guy inverse, which I have here. So there was an example which I showed in the first session where we can do some really, really simple inverse problems using neural networks because I mean, inverse problems are horrifically nonlinear. Typically, our forward problem is simple or even linear. But I mean, we're already starting from something which is horrifically nonlinear. So turning it into an inverse problem is kind of cheap. So what I'm going to do is I'm going to consider the problem, which is u prime prime x plus c u your u prime. Yeah, plus c u prime x equals fx. I still have my Dirichlet conditions. But this constant c is going to be unknown. Okay, what I'm going to say is that somehow I know that the physics of my system is ruled by this equation with some unknown parameter, but I have some measurements of my solution and I want to find this parameter because for whatever reason, it interests me. Okay, this is like a really, really toy inverse problem. So I also have some samples, let's say xj, uj, where this uj, this is my real solution that I have in my lab that maybe has some kind of noise measurements. Okay, so this forward problem, if I know my C, this is just a classical linear first order ODE. We can write the solution by hand, right? Going backwards, now this becomes a much more complicated problem. But at the level of this kind of implementation, again, a lot of the stuff that I'm saying, this is in principle. In practice, it might take a lot more work to get a reasonable solution, but I can very easily implement a loss function that gives me this inverse problem doing barely any changes to my code. Okay. So I'll just show you how this works. So I have my pins loss, which I defined here. So up to here, this is just what we would have if we have a regular u prime prime is equal to f kind of problem, right? Now, for my inverse problem, so I have another thing which goes into my class when I initialize it, which is inverse false. Okay? So if we put inverse true, this means I'm also going to be trying to solve my inverse problem. And what happens here? So I load my x data, I load my y data, and I define a new variable, which is this c, which I want to find. Okay? Same way we would define any other variable. And because I want to see how this c is evolving, I'll just define another list so I can record its value during training. Okay. Now, what do I have to do to change the loss? If I go down to loss pins, so what I have here, if I'm trying to solve my inverse problem, well, I have my ODE, which is now basically the same thing, but now I have this unknown constant here, which multiplies my derivative. Okay, so calling this is the ODE we want to solve. I define another bit of my loss, which corresponds to trying to match the data that I have. Okay, so y data would be these uJs, x data would be these xjs. In fact, I'm going to put it to the power of 0.5. Then I define my total loss to be loss ODE, which corresponds to trying to solve the pins problem, plus loss data, which corresponds to trying to match my solution to the data. Okay? That I have no idea if this is actually a well-posed inverse problem, but this is just to show you, I mean, how easy it can be to implement these kinds of ideas within these kinds of frameworks. Okay. Now, so once I have my loss function, okay, I could put some weight here. I probably should put some weight here, but this is just to show you how the things work. Once I get down to defining my gradients, I now need to have in mind, I have some other variable which is floating around, right? This unknown constant c, which in reality is the thing I actually want to find, right? Maybe I don't actually care about the solution. I just want to find this constant. Well, of course, I need to update the constant as well, according to this optimization principle. But again, this is a really, really simple change. So remember, umodel.trainable weights, this is a list of tensors. Okay? So if I want to take the gradient with respect to a list of tensors, well, I put the loss and my list of tensors. I just need to append this list with the other tensor, which in this case is just a scalar variable, essentially, into my list. So I just do plus self.c. Okay, so now I have a list with another element which corresponds to this guy that I want to find. And again, similarly, not only do I want to find this derivative of my loss with respect to this unknown parameter, I need to update it as well. But again, this is just a tiny, tiny little change to my one-step process. If I'm trying to solve my inverse problem, well, then I just apply my optimizer to zip. So G now also contains the derivative of my loss with respect to this unknown constant. And I need to specify the list of variables that I'm updating. So I put the same thing there as well. Yeah. So I mean, these are how many lines of code changed in order to go from a forward problem to an inverse problem? It's like 3, right? And whether this thing is actually going to work now that I run it, this is a different story. Okay, this is based on a pins formulation. Make sure I've got my cutoff function. Okay, so I'm not sure if you can see it very clearly here, but it's also printing out the value of this C. So the data that I chose corresponds to C equals 0. Okay, and what we can see is, okay, we're in the realm of errors of, okay, ignoring all of the noise that appears to be turning up. But I mean, we're not doing a bad job for something that I haven't optimized in any way, shape, or form. Right? Yeah, so look, now we're in the realm of a couple of percent error. And as well, I mean, the computational cost of doing this, there's absolutely no difference effectively from the problem that I started with. So, I mean, trying to solve this is something that I wanted to emphasize at the start. I mean, if you want to solve something like an ODE or PDE in very low dimensions once, then there's really no sense at all in using neural networks because I mean, something like finite elements or finite differences, I mean, these are much more robust. You can do a posteriori error estimation. You can get very accurate solutions. Okay, maybe there's a scalability question, but you know what the limitations are very, very clearly. If you're trying to use a neural network to solve these kinds of problems, you're introducing so many moving parts that it can become very difficult to get precise solutions. And the benefits of trying to use neural networks is that this training process is no harder in any sense than training the solution for the forward problem. But solving the inverse problem, I mean, you basically just do 2 or 3 changes of your code, and we end up with a solution where my error is of the order, like it should be 0, I get 0.02. I don't think that's too bad for a very ad hoc implementation. I think for that, I mean, that's more or less all I wanted to say on this. I mean, are there questions? Are there comments?
Session here at the coffee break, and we will resume at 12:50.